It is my great pleasure today to introduce to you Carlo Rovelli, who obtained his PhD in Italy and moved on through postdoctoral positions in the US, Yale and Pittsburgh. Now is a professor in Aix-Marseille, leading a rather large quantum gravity group. The achievements, I won't list them all, but most of you here will know some aspects of the work. He's one of the co-founders of Loop Quantum Gravity. He worked on physics without time, eliminating this mysterious parameter. He came up with Relational Quantum Mechanics, a way of interpreting in a self-consistent way quantum measurements and quantum mechanics itself, and has written many acclaimed books on the philosophy of science and quantum mechanics and the nature of gravity. And so, without further ado, I will ask Carlo here to tell us about scientific realism. Thank you.
Thank you very much. This nice introduction. Thank you, all of you, for being here. In fact, so numerous. I was expecting a small class. I found it great. Audience is fantastic, so thank you for coming. I'm going to talk about quantum mechanics, and I'm going to talk about scientific realism a little bit. Mostly, I will talk about what I call relational quantum mechanics. I'll explain what it is, which is one of the many possible perspectives from which you can view this strange beast, which is quantum theory. So let me start from just a few words about the general problem. Quantum theory, of course, works fantastically well. The great news is always, oh, quantum mechanics works. And it goes out in the newspapers every time we find out that it works the way we expected it to work. But the range of different opinions about how to think about quantum mechanics is staggering. People talk in a convincing way about quantum mechanics, saying opposite things about the world. Okay? So I will not try to define what the problem of quantum mechanics is. Just listen to different people. Go to Vienna, go to Oxford, and you get completely different stories about quantum mechanics, what quantum mechanics is about, and what it's saying about the world, and how to think about it. I'm not going to solve the problem. I'm going to tell you a little bit about the landscape of views about quantum mechanics, and I'll insist on this particular way, relational quantum mechanics, which I want to present it just as in a family of similar interpretations, which are to some extent refinements of the so-called, vaguely called Copenhagen interpretation of quantum mechanics. There's no Copenhagen interpretation of quantum mechanics. There are things written by Bohr, by Heisenberg, by others which differ from one another. There are textbooks. There's a sort of consistent story in quantum mechanics textbooks that makes many people unhappy. And, and there are variants of that, including relational quantum mechanics, and including, of course, the idea of Anton Zeilinger, who is there, who came out roughly at the same time and has a lot in common, but some differences with what I'm going to say here. So, relational quantum mechanics originated in a paper in '96, so it's quite some time now, a lot of time. For a while, it was pretty much ignored by everybody. I was very disappointed because I thought it was a great idea and it went completely flat. But then papers came out about it, first from philosophers, then from physicists, then from mathematicians. It sparked a number of different works, and I would say now is on the table among the possibly consistent, but with a price, I'll come to that, ways of looking into quantum mechanics. One of the things that started is a variant of the problem of the reconstruction of quantum mechanics from a simple set of physically motivated postulates. There have been remarkable advances in that direction, particularly Philip Hearn, and I will not go much into that. I will mention that at some point. Information plays a role in this discussion, and this connects to what Anton Zeilinger has been saying for a long time. I will be more specific. So that's just as an introduction. Let me start by saying what is the problem of quantum mechanics by listing different ways of viewing the theory. And I think very roughly one can find 4 interpretations that today are most discussed. How should I write them here? So one, as I said, is the Copenhagen interpretation, in which essentially you think about systems. That's what is written in textbooks, right? The quantum systems, where they are, system. And according to the textbook story, you measure them. So there is some observer with some apparatus, which is a classical description, nothing quantum mechanical there, which make a measurement and come out from the measurement with some values Qn of some quantities that describe the system, right? Spin is up of this particle, or spin is down at some time. And then if you have enough of this Qn at some time, you can actually predict what you will measure at some later time, so Q tilde n, at some later time, Q prime, or Q at some Q prime, by writing a wave function and making an evolution, and then there's a collapse. More or less, that's what you read in textbooks, quantum mechanics. And of course, now, a second, completely different way of looking at the story, which is very popular today among some people doing cosmology, some string theorists, mainstream theorists, all the philosophers in Oxford. Oxford is the center of that, but also some philosophers somewhere else. It's called many world. Each one of these interpretations come in variants, right? So keep this with a grain of salt. So the idea is that there's no observer, there's no special Qn, there is no collapse, nothing of the sort. There is a quantum state, wave function, which evolves unitarily in time. And that's it. And from this universal wave function that evolves in time, all the rest follows. You just have to be sufficiently smart of readout of this quantum universal wave function or quantum universal state, read out all that come up, including probabilities, including eigenvalues, including measurement, including collapse, everything. And the main idea is that the wave function never collapses. So if you're measuring the spin of a particle to a tangella, the wave function has actually 2 branches, one spin up, say that goes up, and one spin down, say that goes down. And when you measure it, you yourself, your wave function, get entangled. So the universe as a whole branches in 2. And why we see only one? Because we happen to be sitting in one of the 2. So the actual spin up or spin down is perspectival, depending where you are. Okay? The third family of interpretations is Bohmian interpretation. Where the idea is that yes, there is a universal wave function, but there is also a continuous value of all the physical variables. In fact, not all the physical variables, some physical variables, not all of them, say position and not momentum, for instance. So you have for a particle, for instance, you have the wave and the particle, you both have. And Bohm, somehow following the lead of de Broglie, found nice equations for the particle once you have a wave function that solves the Schrödinger equation. So this solves the Schrödinger equation has its own dynamics, unitary dynamics, and in the wave function there is a particle that moves and is guided by psi, and given psi you can find the equation for Q, and it turns out that the theory, what you see is Q, and it turns out that the theory is actually equivalent. The prediction of the theory are equivalent to the prediction of quantum mechanics. The fourth and last in this super simplified list of approaches, it's a physical collapse. And here, rather than interpretation, I should rather say physical collapse theory, or theories, plural. Because this is a number of approaches that actually say, well, collapse doesn't make sense in terms of standard quantum mechanics. It has to be understood physically, as a physical process, mainly as a correction of the Schrödinger equation. Schrödinger equation is the unitary evolution of the wave function, but actually, let's imagine that the Schrödinger equation is not the whole story. It has other terms, non-linear terms, such that the wave function of a particle, say, once in a while, it collapses in some point, following some dynamics. The two most well-known variants of it are WGR, Weber-Girardi, Rimini, in which they have an actual mechanism that does that, and Penrose, which has some hand-waving arguments that gravity does this job. Once you try to put, once a quantum system interacts with gravity, with space-time, if the space-time goes in a quantum superposition, it doesn't want to be in a quantum superposition too much, so as soon as you quantum superpose in space-time too much, it collapses to just one, so it keeps collapsing. So these are that's what most is on the table. And I'm sure many of you will think, oh, you're missing this one, or you're missing this other, but that's mainly the ones which are most discussed, if you want. When you go to a conference on the utilization of quantum mechanics, usually at the end there is a vote. These are the ones that get many votes. So, let's make it concrete. Suppose I had a radioactive particle, it's the bits of uranium, a radioactive piece of something there, and I have some some Geiger counters here. You wait for a while, some initial time t0, this is still radioactive, and some later time one of these clicks. Click. Okay, not the others. So, according to the first story, well, you first have some measurement of this, and then later on you have some measurement of this clicking, and you do your calculation. You have a wave function that you can model this with a particle inside a box with a potential that traps it, but the potential is finite height, so you can tunnel out, and so the wave function leaks out. So the wave function, it's all over, right? That's actually the first discussion given by Einstein about the problem. Before EPR, before anything else. Then from there we evolved to EPR. And then, at some point, there's always a probability that some of this clicks, and at some point, whoop, this disappears. Suddenly, that's a collapse, and the particle is here, the wave function is concentrated there, and then it's out again, the Schrödinger equation. So that's the Copenhagen story. The many-wall story is that there is this wave, okay? And then, at each time there's a probability of one of these to click. So at each time the wall splits in different universes, and at each time it splits according to whether one of none have clicked or one have clicked, so there are all possible universes, all real. If you go to Oxford, you will believe that strongly. I mean, Simon Sanders, David Wallace, all these people really believe that. There are all this enormous number of universes. And they tell you that unless you believe that, you don't believe in realism. So you're not a realist. This detector here hasn't clicked. It's just there are many, many worlds in which in some of this it has, in some of this it hasn't. It's a continuous of world. And there's a long, complicated story from this continuous of world to talk about probabilities and talk about observing. The Bornholm story would be totally convincing if there was only one particle in the world, but there are many particles in the world. But the Bornholm story is that there is the wave governed by the Schrödinger equation, but there is also a particle that moves guided by the wave, so no surprise that we see the particle at some point. Why there is not just a particle? Because of course if you put something with two holes here, then where the particle arrives depends on interference, and just the particle alone doesn't work. You want the wave. So the Bornholm idea is that of course there is the wave because of interference, but there's also the particle because you see the particle in one point. And the physical collapse story is what I said before. So the wave function starts, but then suppose this particle is sufficiently heavy, at some point the wave function just boom, concentrated here, and then boom, concentrated here, and then is clicked here. More or less, I'm just making a cartoon of this story. You see, there are completely different stories about what happened in the world. They're all good. And in fact, for each one of these stories, there are very smart scientists that believe them like a religion. And they're ready to fight all their energies for them. And they're very smart philosophers that believe that that's the only possible way of viewing it. So they're not contradictory, they're all possible. But for each of these stories, there are a lot of other people, usually many more, who just think this nonsense. So it's a strange situation. Why are we in this situation? Because each one of these perspectives forces you to accept something. Each one comes with a price, a cost. It could be a philosophical cost, it could be a physical cost, cost of different kind, which everybody else, the people who don't like that particular perspective, consider it too high a price to pay in order to make sense of quantum mechanics. So let's go through this very, very rapidly for each one of these interpretations. Let's see what the cost. Let's start from here. Well, the price here is that the standard way of presenting things, at least, is that this guy and his apparatus are treated classically and not quantum mechanically, which is disturbing. I mean, it was okay in the 30s when we just invented quantum mechanics, but now we know the world is quantum mechanics as a whole. Why can't we give a quantum mechanical description? But even more, all the idea is that there's a measurement. Now, the very idea of founding a description of the world in terms of measurement, it may appeal to people who does experiment in laboratory, anatomy, but other theoreticians who want to describe the full universe. Okay, where there are no measurements, I mean, on Andromeda, presumably, I don't know, but if nobody will make a measurement, what's going on? Where is a measurement done? What counts as a measurement? Unless this is said clearly and cleanly, the thing is shit. You want a theory that works about early universe, about galaxy formations, that quantum mechanics affect all over. When does it count as a measurement? Of course, it can be cleaned up, but that's the point. I want to clean this up. Right? So what is a measurement? And what is an observer? And of course, here immediately you see that philosophy comes in, because if you're a realist, if you're a naturalist, much less than a realist, if you believe that we humans are just part of nature and we have to understand ourselves just a part of everything else, and it is complicated, then you cannot start with fundamental theory by putting a subject. If you're in Germany, or in a German-speaking country, and idealism has been the dominant philosophy for a few centuries, you think the subject, it's before everything else, everything refers to, you come from Fichte, Schelling, Hegel, then it seems completely natural that you think in terms of the subject. Okay? But even German philosophical world, there's a big reaction against this strong idealism. When you think about the world, not when you think about the theory of knowledge. So, do we really want a physical theory that requires a mind which is sort of outside the universe to think about it, and we a priori cannot describe this mind in natural terms? So you see immediately there is a philosophical side of it, but it's clear that there's some cost. And what about the many world that the Oxford crowd like so much? Well, the cost is huge, because you have to believe in all these extra universes, extra world, equally real as us, just to make sense of what happens here with just a spin particle that goes up and hits the screen. So the cost here is, I would say, a hugely inflated ontology. Worlds and worlds and worlds, but I think the difficulty is stronger. This is always said, but I think there's a stronger difficulty, which is what are the actual QN? What is the particle being here exactly out of the pure wave function? This is a long technical detailed discussion, but I don't think they have succeeded, in spite of the beautiful books by David Wallace, by Saunders and by others. I don't think if you just have the wave function, out of that you can deduce this is a glass here. There's no glass here in the wave function. The Bohmian theory is wonderful. This has a fantastic. First of all, it's deterministic. You have the thing you see. You have the thing that satisfies the Schrödinger equation. It seems wonderful until you go into it. Once you go into it, you find two difficulties. One is that it's a funny determinism, and it's a funny realism, where there's a part of reality which is hidden from you in principle. Okay? So the determinism comes from the fact that it's impossible to have knowledge about this and that from what you observe. So it's a strange price, realism, when it's hidden by the theory itself. So hidden part of reality. But worst, once you try to make it work, you have to break Lorentz invariance badly, and you have a lot of difficulties of just working out spin. This wave function is not in space-time, but is in configuration space. For quantum field theory, this is the function of the space of all fields. Okay, and then you don't know exactly what these are, because the people who do Bohmian for quantum field theory are confused how to do it. It's, for a physicist, it just smells wrong all the way through. You have to believe that there's a wave function that actually determines things instantaneously in a fixed Lorentz frame that is in principle undetectable. It's just bad physics. So it smells wrong. And the physical collapses theory, well, I mean, if there was a hint, an empirical, experimental, whatever suggestion that actually the collapse happened, but there isn't. I mean, you can make a parameter there and make the parameter as small, as invisible as you can. So there is no empirical support whatsoever. And frankly, none of these theories look very appealing as a theory of nature. Once you look at them, they are sort of proof of principles that something like that might work. But Pegnon's theory, you cannot make it precise. People have tried. And WGR, you can make it precise, but come on. I mean, this is expertise that. Again, these are not. Nothing of this is deadly, and in fact, none of this is dead. But each one of these are strong reasons for which many people don't believe in this, don't believe this, don't believe. So that was part one, and now let me come to the relational story, which I would, like Zeidinger's idea, frame as a version of Copenhagen when we try to solve and take away the ugliness of Copenhagen and make it consistent. So I would put inside here both Anthony Hughes and Archuleta. And that's what I'm going to talk about. Now, to talk about that, I'll start from some history, and this is going to be hard because I'm in Vienna, I'm in Austria, and I have to say something bad about Schrödinger. So I don't know how I thought they say something about diabolical radicals. So, but I'm going to do it. So here's the story. Schrödinger in 1926 wrote a paper, of course, in which he did something fantastic. Out of sort of first principles, he computed the spectrum of the hydrogen atom. Right? Boom. And all this is based on an equation, which you all know, except I probably got all the sign wrong or whatever. I'm writing one dimension, so I don't have to put whatever, plus. Where all this is for this beautiful quantity, which we introduced, there is a function in space and time, which is a wave function. Okay? And out of this modulus is a spectrum of hydrogen. Of course, you have to do it in 3 dimensions to the right potential, one of their own. Wow! Except that in 1925, this had already been done. In fact, quantum mechanics, as we study today in textbooks, okay, Rieger, values, evolution, everything, including the spectrum, was done before 1926. Right? It was done by a bunch of people. First of all, by Heisenberg, who in 1925 wrote the paper that actually started quantum mechanics, an incredible paper, just mind-blowing paper. And shortly after, he himself, so Heisenberg, plus Jordan, who had the misfortune of being a Nazi and so not having a good press in his life, and then born, developed a theory in a sequence of papers which are incredible. There's all angular momentum theories, everything in this paper. It's just what you find in modern textbooks of quantum mechanics is in those papers, everything computed. And they have, in fact, one got the idea, the main equation, right, PQ commutator equal IHR, I'm not sure of the sign, minus, doesn't matter. And if you start from this equation plus h equals p squared root 2m plus v of q, okay, and you find the eigenvalues of this where the 2 operator satisfies that, in principle you find the spectrum of hydrogen. Not in principle, because it was found that it was computed by Pauli. It's not an easy calculation. You know the story. They tried hard, 3 of them, and then they said that because already Heisenberg and Born had asked Pauli to help them to do this paper, and Pauli said, no, I have more interesting things to do. But then when they wanted to compute, they put here 1 over r, and they wanted to compute the spectrum of the hydrogen. It was horrendously complicated, this calculation. So they went back to Pauli and said, can you help us? And Pauli said, that's too hard for you. And he did it. That's Pauli. And in the middle, of course, Dirac also got the paper by Heisenberg and had the full understanding of the relation between this and the Poisson bracket, and the idea that the observable quantities are the eigenvalues of the greater cube, half or greater. So it's all. What has Schrödinger done? Well, got the Nobel Prize, and Einstein suggested he got him and Heisenberg the Nobel Prize. So it's not nothing. But from this perspective, what has he done? First of all, he has transformed a hard algebraic problem in a language that at the time the physicists were completely unaware of. You know that Heisenberg had no idea what matrices are. Now we do linear algebra at school, but Heisenberg didn't know what these things are. He just put in this system, invented this thing of multiplication without knowing that it was already studied by mathematicians. It's Jordan that told Heisenberg. So this is a very hard mathematics in the 30s, in the 20s, for the physicists. Even today, people are not at ease with non-commutative algebras. But that's non-commutative algebra, right? With non-commutative algebra, you compute spectrum of operators in non-commutative algebra. So Schrödinger, without knowing that, because he did it independently, I believe, he translated a tough algebraic problem in a nice partial differential equation problem, which is the language that everybody knew at the time, because of Maxwell equations, because of heat equation, because of all the stuff that the French mathematician, etc., recommended has done. Maxwell everybody has. So first of all, he translated into decent mathematics, and he gave an intuitive picture of what goes on. Because this is something very simple, right? Instead of the electron, you have a wave. And then the connection with what you measure was not completely clear, but you have a wave. So immediately it did catch on. It's much easier to do computation with the Schrödinger equation than doing computation with that, just took over. Immediately Heisenberg started complaining, saying, what the hell, this has nothing to do with quantum mechanics. You're wrong. And he saw immediately the difficulties. Difficulty being, first of all, that the nice idea that this is a function in space and time just is dead as soon as you have two particles. It's not a function of space and time anymore, it's a function of configuration space. It's a function of x and y. So it's a function of many legs. Okay? But it's more than that. The connection between this and the fuse and what you see is far from obvious. The discussion was raged for very strongly at the time, and Schrödinger, who, let me now try to wake up, has been one of the clearest minds in this discussion. He's one of the people who more clearly went through the full discussion of the linear quantum mechanics. This is what he writes in the 50s, much later. This is from a conference he gave in Dublin with Schrödinger. He says, the creators of wave mechanics, the creators of wave mechanics lulled themselves for some time in the hope of having cleared the way to a classical physics-like description of a continuum. Right? We thought we could have transformed everything just as a continuous. But, this is Schrödinger, the hope turned out to be false. Nature rejected the continuum description. And then from the same text, in another paragraph, discontinuity reappears in the connection between the wave representation and the observed facts. there is no univocal correspondence between the two. In other words, if you just have the Schrödinger equation without the projection postulate, without the invalid postulate, without the flux postulate, without all the rest of quantum mechanics, which is actually the core of quantum mechanics, you don't have quantum mechanics. Schrödinger talks about continuity and discontinuity, and I think this is really crucial. And I want to here before entering in the actual discussion of relational quantum mechanics, let me say something about discontinuity. I am shocked by the fact that many of the discussions about quantum mechanics forget the discreteness which is core in quantum mechanics. The name of quantum mechanics comes from this discreteness. The levels of the hydrogen atom are discrete. The photons are granular manifestation of light in some appropriate sense. Angular momentum is quantized. Discreteness is all over quantum mechanics. In fact, one can make this more precise. In phase space, if you know that the system is in a region of phase space, finite dimensional region of phase space, say one-dimensional system, and you have a quantity that measures where in this region the system is, this quantity can only take a finite number of hours. Why? Because the dimension of phase space is action, right? It's PQ, and each bar is the unit of action. Each bar is sort of the smallest region in phase space where you can squeeze your knowledge of where the system is. So any quantity that tells you, wait, for instance, I don't know, the energy, you know that a pendulum has an energy less than some quantity. How many alternative states would there be? Well, that's a finite region of phase space, so there's a finite number of possible distinguishable alternative states, therefore energy has discrete terms. This is universal, this is general quantum theory. So discreteness is a core of quantum theory, and it's completely, all these views are completely blind to discreteness. They try to recover it wave habit. There's no discreteness inside unless you put it in the interpretation. Of course, there's discreteness on the eigenvalue side, but the connection between the energy and the frequency, it's something else. It's not written in the Schrödinger equation. So continue to this core. Oh, sorry, discontinue. This core. All this was introduction, then it goes to, but all this, of course, served to introduce the main idea of relational quantum mechanics. So what are the main idea of relational quantum mechanics? The main one is forget the wave function. Forget the idea that the wave function is an actual description of what is happening there. I believe that in Vienna, this message can go through a little bit better than elsewhere in the world. Because in many parts of the world, if you go to Oxford, Cambridge, Santa Barbara, Boston, or New York, people look like, okay? People say, quantum mechanics is a wave function. What else? Okay? Quantum mechanics is the Schrödinger equation. What else? There's nothing else than the Schrödinger equation wave function. I believe that this is totally misleading and is actually the source of our confusion about quantum mechanics. The source of our confusion about quantum mechanics, I think, is taking the wave function as the thing there. Wave function is not the thing there, right? The classical approximation of the wave function is the Hamilton function. The Hamilton of the action as a function of the initial and final points in space. Nobody would think that the Hamilton function is the actual thing out there, right? If I do the classical mechanics of this, it's that I have the Hamilton function all over, but it doesn't mean that there is something actual all over. We're talking about realism. The Hamilton function is a way I have for predicting where I'm going to see this, but it's not in actual stuff. So the wave function, if you want to know the meaning of some quantity in a theory, just look at the approximation of the theory where you understand it, and you get it. So the approximation of the theory where we understand it is a classical approximation, and here we understand it. There's nothing ontological in the wave function. If this is right, we have to divide these ways of thinking. We have to go back to the QL. Quantum mechanics is about this. It's about the particle being in a point of some time in some sense. And relational quantum mechanics is the idea, first of all, that quantum mechanics is about units. Okay? I sometimes call it events or quantum events. These are, if you want, the outcome of measurement, but I don't want to talk about measurement because I don't want to bring human there. It's nothing to do with humans. Quantum events happen all over the universe where there are no humans, no measurement, no laboratory, no Anton Zeilinger writing something in his notebook. Okay? So this is the quantum event, and this is the first one. Now, second point. When these are discrete, right? Outcome measurement are discrete. They happen at some time. That's it. Abstract of Heisenberg 25 paper. We understand better the phenomena if we give up the idea that we have to give a continuous description of the position of the particle. We have a position of the particle at some discrete times. The ontology is more sparse than the classical one, not more heavy than the classical one. No more things, less things.
Should we accept this discreteness as the axiom, beginning from that? How we are sure that
We're not sure about anything here. We are trying to make sense of the theory, and my claim is here, let's try to make sense of the theory by first believing that these are the things we're talking about, and these are the things that describe the world. Okay? The outcome of measurements. These are the things that, then I want to understand when do, okay, follow me.
They can take continuously many values. I mean, the self-adjoint operators can have continuous spectrum.
In some cases, they may be continuous, but what I'm sure. No. I'm not taking the value of the. Sure. What I'm saying is that if you have a single particle, the position at each time doesn't need necessarily to be the thing to which you give meaning. There is a beautiful account of Heisenberg intuition in Copenhagen. I don't know if you remember in the play, in which he says, "Well, I was in the park in Copenhagen, behind what is today called the Board Institute, thinking about these things, and I saw a man walking. Remember that? And it was dark. It was the 20s. The park was very dark with a few lamps. So I actually saw the man appearing under a lamp, and then nothing. And then appearing another lamp, then nothing. And then, said Heisenberg, I thought, well, of course, this is a man, he's heavy and big, so I know where he is in between. And then there's a flash occurred to me. That's true for a man, but what about an electron? Do I really know? I see it here, I see it there, I see it there. Do I really know that in between it is somewhere? Maybe it doesn't mean anything. Maybe the electron is this manifestation, and there's nothing else at the story. And that's the intuition at the beginning of quantum theory. In my opinion, quantum theory comes out from this intuition. Now, in the old master's story, these things are manifested when I, the experimental, look. When do the QN, when are the QN become real, actualized? Let's make it simple. What happens when an experimental measure a particle and interact with it? Let's take away the the heavy load of an experimental, being human, being big, being whatever, when there is an interaction. When interaction. So let's say I have system 1, system 2. When there is some sort of interaction, they heat, something exchange, some physical interaction, namely when the evolution of this and the evolution of this are not independent, when one affects the other one, there is a discrete interaction. What variables Qn are actualized? Well, the way the system 2 is affected by 1 depends on some variable of 1. This is the one which is being actualized. Okay? If a screen is hit by a particle, the way the screen is hit by a particle depends on where the particle is. So the position of the particle is what becomes actualized in the interaction. The key point here, difference from the standard interpretation, is that I'm not requiring to be neither Anton Zeilinger making a measurement, nor a physicist, nor a PhD, nor a human being, nor consciousness like Wigner wants, nor an abstract holder, sort of German subject holder of information, or like Fuchs wanted, the perspective on the wall. That's all fine. But I want to say whatever is 2. An interaction between 2 and 1 actualizes the value of 1, and vice versa, of course, which determines how one system affects the other one. No required record, no classicality, complexity, consciousness, or anything like that. We want to do physics. The only ingredients we have is systems and interactions. And here comes the key point. This can be done, this is coherent, at a cost. And this is the main point, and I explain the main point, then we make a small break, and then after that I will talk about everything that goes with it, information and all the rest. So the main point, and I'll use this graph here, is that if I stop here, you would say, wait a moment, this doesn't work. This doesn't work because two atoms interact with one another and then collapse the wave function. Okay? Right. So here is a full story. Let me articulate the objection cleanly. Suppose that one system 1 and system 2, there's an interaction. And in the interaction, a certain variable Q of the system 1 is actualized and take a certain value, say Q equal A. Okay? I'll think of Wigner-Friend situation. I have another system, 3, which at a later time interacts with this 2. Okay? And let me use a standard textbook language, measures a quantity of the combined system, let's say E, which happens not to commute with Q. According to standard quantum mechanics, okay, if 3 knew the earlier state of that, had interacted previously with this thing here, and want to compute the probability distribution of the possible value of P, 3 must disregard the fact that Q equal A, because in many word interpretation, quantum mechanics predicts interference between the branch Q equal A and the branch Q equal B. Right? So, how do you bring this together? Simply by saying that what happens in interaction is that Q taking the value of A with respect to 2, and not with respect to 3. And that's the relational quantum mechanics. I've said it all. I'll open up and explain what it means. So the story is the following. Think for a moment of the universe as many different systems, just as for the sake of that because of what we do in physics. With respect to one system, the rest of the world appear correctly as is described in quantum mechanics. At every interaction counts as a measurement. Okay? The value of the rest of the system are described by the eigenvalues. The probability distribution are described by transitional to quantum mechanics. With respect to another system also, I believe that quantum mechanics is correct with me. Why? Because all the experiments of Anton and everybody else has come out right for me. So I believe that quantum mechanics works for me. But I also believe it works for you. And I believe that if you make a quantum mechanics experiment of me, I turn out to be a quantum mechanical object. So I just want to take this as a fact that all stay together. Which forces me to face the fact that value of quantity are actualized at some times, because otherwise we wouldn't have measurement outcomes, and we do. But also, when I compute transition amplitudes, I have to disregard interactions when I'm dealing with a composite system. So, in other words, let me make it slightly more technical. This story here has a description with respect to 2 and a description with respect to 3. A description with respect to 2 is that at some time t, the variable q takes a value a, so the system 1 has a state a. But with respect to 3, what happens at time t is that the common system of these two might evolve into a combined state, A for 1 tensor some correlated thing for 1 plus B for 1 tensor some correlated thing B for 2. So I want to say that this description is correct and this description is also correct. This description is correct with respect to 2. This description is correct with respect to 3. Q equal A is true with respect to 2, is not true with respect to 3 in the sense, 3 is not measuring anything, in the sense that later on, when you measure something, 3 should not use the fact that Q equal A because there are both branches still needed to compute a probability amplitude. When we want to measure the distribution probability for P, he has to compute some eigenvalue of P, so we call C psi, modulus square, and then there is the interference between this term and this term. So, the moral of the story is, let's take quantum mechanics at face value with respect to any system counted as also. Okay? That's relational quantum mechanics. There is a lot to say about that. There is a clear advantage, there is a clear cost. So let me just make a list of advantages and a list of costs, and then we make a break, and then, as I said, I'll discuss the relation of that with information, which is nice, because now you can look at information from the perspective of 2 or from the perspective of 3 and see what is in that dictionary. And I'll talk about the reconstruction and a few other things. But let me just close this hour with a list of advantages and costs, so plus and minuses. The plus are clear, in my opinion. There is no many worlds, just one world where things happen. Okay? We don't have to assume that there are all sorts of worlds. There is nothing hidden, and there is nothing that brings Lorentz invariance. There is nothing that's physical. There is no physical process that we're assuming that we haven't seen yet. There's nothing of the sort. It's just quantum mechanics. Okay? It's coherent, it's consistent, It is consistent. It's 20 years that this thing is on the table, have been looked by everybody. At the beginning, people were saying, oh, it's not consistent. It is consistent. So the plus is none of the other difficulties. Well, so why don't anybody jump on that? Say, oh yeah, that's a clear solution there. Because it's a cost. Okay. So the minus, the cost. What is the cost? Well, the cost is that any statement that we give about the world has to be labeled by an observer. So it is not true. We cannot give a description of the world in terms of unlabeled fact. This is here univocally as a description of the universe. This is there univocally description of the universe. And make a list of all of this. Because if I see this here, maybe you can have made measurement in the past and measure in the future, such that in your calculation, it turns out that I'm in a superposition of this here and me believing is here and this there and me believing is there. So every statement about the world has to be related. That's why it's called Relational Quantum Mechanics, to a system with respect to which it is true. Which system? The system that interacting with the chalk has got the information that chalk is here and chalk is there. So it is a realist interpretation, but it's a weakened realism, because unless you fix the perspective, the point of view, you have to live with this relational aspect of variables. In physics, we have a lot of relational variables, like velocity. Velocity is not a property of an object, it's a relative property of two objects. But it's a big jump to say that all the variables, all the contingent property of objects are relational. So I've given you the main idea. I suggest we take a 5-10 minutes break to breathe, so you can start digest that, and then reconvene, and I will ask you to talk about information. I will translate that in the language of the information field. Okay. The second part will be shorter, and then we'll have a reasonable break, and then there's a question section. Some of you came and said, but this is the same as standard quantum mechanics. It is very similar to standard quantum mechanics. It is standard quantum mechanics. But the way I think about it, it's taken seriously quantum mechanics and the consequence of quantum mechanics when we include the fact that the measure and the apparatus can always be viewed as quantum systems. So the difference between quantum mechanics in the way it is usually described in textbook is that, and this is also the difference with cubitism, Hooks and company, is that instead of assuming an observer that looks at the world, make measurement, and sort of collapses the wave function, gets values, actualizes physical variables every time you interact with the world, instead of that, I think there are many, we can view the world as many systems, many subsystems, interacting with one another at different times. And quantum mechanics is true with respect to each one of them, meaning the actualization of the variable of this system with respect to this system happen when there is an interaction here, but does not happen with respect to this system or this system or this system. So in the language of standard quantum mechanics, when you make a measurement, it is true that then is a fact that the spin is up if I've seen it up, so I've collapsed the wave function to spin up. With respect to me, now everything I measure in the future is determined by the fact the spin was up. So I can collapse the wave function to do the next calculation. But with respect to anybody making a measurement, including me, it is still true that nothing has collapsed. So in the calculations, the wave function I have to take into account of both branches. Spin up, me seeing spin up, plus spin down, me seeing spin down. Because the interference between the two, it's real. It's predicted by quantum mechanics. Which is a short question, yes, otherwise it's a long we go. Between? Yeah, that many words. Infinite. In many words, it's just a wave function. Well, just psi. And there's never assumed an actualization of variables. I'm saying that with respect to every system, there's an actualization of variables. The ontology of many words is psi. The ontology of relational quantum mechanics is relational psi. So it's the opposite ontology. I'm saying what confuses us is giving value to psi, even ontological weight to psi. The theory is not about psi, it's about variable having value. This being here now, the electric field being pointing that direction, this being black and this being white. That's what the theory is about. But these quantities are all like velocity, relational. So this is white with respect to me. This is black with respect to me, and so on. Okay, this is here with respect to me and with respect to me. Good. So, first of all, is this a solid system? What is the relation between perspective? Perspective meaning, what is the relation between a variable q being equal to a, say, with respect to 3, or q equal to a with respect to 2? How is the world seen by me and the world seen by you? Am I saying that every physical system has a perspective about the rest of the world and they don't talk to them? No, obviously not, right? Because physical systems interact. Let me put it very simply. Suppose you measure the speed of a system and measure spin up. Now, I, as a physical system, I'm topologizing everything. I can measure spin up, but I can also ask you what have you measured. Okay. So nothing prevents you and me to communicate. And I ask you, what have you measured? So I've just erased from my perspective, the combined state of you after the measurement is spin up times 1 times you having seen spin up plus spin down times you having seen spin down. So if I ask you what have you measured, I'm measuring this variable here. So from my perspective, if I ask you what have you measured, I measure this operator here, and I can get either this answer or this answer. And from my perspective, I then projected the state either here or here. So if after having asked you what have you measured, I measure the spin, I get the same result. So quantum mechanics is nicely coherent. There's so much structure of quantum mechanics that nicely work to make the different perspectives coherent. Of course, if I measure a quantity that does not commute with what you measure, then this doesn't work anymore. And there is an incoherence. But that's the quantum mechanics Heisenberg relation. That's the fact that information is the system, or whatever you want to read it. So in other words, systems can communicate with one another. They won't look the same to all systems up to the quantum mechanical certain information. Not exactly, up to H1. Okay. Now, information. I know that Anton is very keen of thinking about quantum mechanics in terms of information, and there is a lot of people who think about quantum mechanics in terms of information, the qubit people, and so on. It all started with John Wheeler, who is the first one who said, look at information if you want to understand quantum mechanics. John had all sorts of fantastic ideas in all sorts of physics. And was vague about that. Nothing precise. But wrote this famous text, it from bit, in which he was trying to reduce entire physics to information. I was strongly influenced by John Wheeler, not only quantum gravity, but also in thinking about quantum mechanics. In fact, my 96 paper, it has a long second part about information and has postulated quantum mechanics in terms of information, and it came a lot from John Wheeler. And then my paper was picked up by Fuchs, and it was picked up by other people. As far as I believe, Zeilinger and myself didn't know about one another. And we came out with the same two main postulates. I think they're the same. Are they? More or less the same. More for a physicist like me, let's say, for a precise person like you, I'll say what the postulate are. I think that Anton, I don't know, was also under the influence of John Wheeler, or at least got something that was in there a bit from some. So what do we mean by information? The notion of information is tricky because information means all sorts of things. And it's very slippery because it's used, I mean, you have a USB key. How much information is there? Well, there is 1 giga. No, there is nothing, it's just all scrambled. It's both correct, but we're using information in a different sense. There is a common use of information which is mental, is knowledge. So it requires a subject, it requires to know what is knowledge, what is, so that's sort of high-level meanings of information. There are more physical meanings of information. There is, in fact, one version, maybe we should have different names because this is a source of confusion. But there is one very simple version of the notion of information, which is relative information, which comes from Shannon, and it's not the first definition of information that Shannon gives, but it's in his text, page 12 or whatever. And it's just correlation. So physical information, there is a notion of physical notion of information. Physical information. Let me try to define it clearly. If you have two systems, this system and this system, and both of them can be in some number of states. Okay? So this is physics system that can be in a number of states. Suppose that this is in some hole that can be like that or like that. So there's two possible positions. Okay? And this also, suppose it can be like that. So there's two possible positions. So together they can be in 4 possible positions. Right? 1, 2, 3. Now, you see the information, if there is something physical tying the two, okay, with a piece of iron, such that they can be only like either like that or like that. Okay? Take the magnet. One hand can be north or south. The other hand can also be north or south. But they cannot be both north or both south. It's a physical thing, which is the Maxwell equation. that imposes this is north, this is south. Okay? If there is this connection, this physical connection between these two, okay? So between this and this, we say that that's Shannon, that there is relative information between the two. And technically, you take the number of states of this, 2, the number of states of this, 2, you multiply, 2 by 2 is 4. If the number of states of the combined system is less than 4, just 2, then there is relative information. So information is the number of states of this times the number of states of this divided by the number of states of both of them. You get 1 is more information, is more than 1, you get information. Or more precisely, first is log of that. Because you like log when you talk about informations. So physical information is just is just that between two systems. So you have two systems, and you have n states here, n state here, so let's say n1 and 2 states, and the combined has n state. This is log of n1 times n2 divided by n. Okay? There's nothing mental, nothing unknown, nothing extra physical in this particular notion of information. It's just correlation. Now, look what happens in relational quantum mechanics. Information comes out sort of twice, but in a clean way. Because let's go back to this prototypical situation in which I have system 1 and a system 2 which interact, and some quantity is measured, and Q is equal to A. I can say, a la Zeinger, that 2 has information about 1, and the information is that Q is equal to A. In a sort of intuitive notion of information. Okay? So, as a result of a measurement, a quantity has taken a certain value, and now 2 knows that the quantity of this value, the outcome gives us information about the state of 1. This is information, this is what quantum theory is about. The information that 2 has about 1. In this intuitive sense, quantum theory is about information that 2 has about 1. But let's look at this from the perspective of a third system. And suppose that the first system knew the initial state of this combined, which was a tensor state. What happens when there is interaction? Well, we know that the standard analysis of measurement that you do in quantum mechanics measurement, what happens is that an initial tensor state may evolve in a correlated state, the one I've written over and over again, this state here. Okay? What does this state is telling me? It's telling me that these 3 measures up here, and then measure, say, the quantum variable, the corresponding state of 2. If he sees this, he sees this, he sees this, he sees this. So in other words, when 3 makes a measurement, the possible state of the spin in 1 is up and down, the possible state of, say, the pointer variable is up and down. 2 times 2 is 4, but of this 4, only 2 are realized. So, there is a correlation between 1 and 2 in the sense of Shannon, in the strictly physical sense of Shannon. So, from the perspective of 3, the effect of the interaction is that 2 has information about 1 in the sense of Shannon relative. careful, there's a slight difference between these two statements, right? This is a physical statement about the existence of a correlation. It's a physical property of the coupled system. The coupled system is such, after the measurement, that it becomes correlated. But the fact it becomes correlated translates easily into what we say that 2 has information about 1. And represents what we do in the laboratory when we take a measurement and we get information. The slight difference is that in one case, there's a difference between knowing that 2 knows the spin of 1 and knowing what is the spin of 1 that 2 knows. If I know that if 3 can compute that the spin is this one, 3 knows that 2 knows the spin of 1, but doesn't know which one. Okay? So why this discussion? Because I think that information is a very useful concept for thinking about quantum mechanics, but I don't think that I think that the world is a world. It has properties. It has quantities, variables that take values, and the key message of quantum mechanics is always taking values is relative to systems. Now we can express this in saying systems have information about variables, but we shouldn't get confused from the fact that then information comes with all sorts of heavy mental, psychological recording properties which have nothing to do with physics. Okay? So, yes, we can rephrase everything in terms of information theory, but I have a certain difficulty of saying, well, let's only put information at the basis of everything, because if I start from that, I don't know what information is. I do know what information is if I take Shannon definition, but then information is defined in terms of system having values. So before information, I have the variables and the possible values that they can take. So the foundation is variables having possible values, not information by itself. Given that, and given that nevertheless, I do think that information is it's a good way for describing the general structure of quantum mechanics getting asked about the world. Mauro Dorato has clarified that, in my opinion. You probably know Einstein's difference between constructive theories and theories in principle theory. I don't remember how it goes. Especially, I think it's a principle theory. Electromagnetics is a constructive theory. So you can give physical theory by giving the dynamics, or you can write down some general principles and then have something you think you know about nature. Einstein considered the principle theory as a very approximate description of the world, and a constructive theory the good one here to go through. Especially I think it's not a constructive theory. It's a general idea about how the world should be, but that has to be implemented in a complete theory. Now, when you do a constructive theory, you have to list down your variables and the dynamic equations. Electromagnetics, you say, well, there is an electromagnetic field that satisfies this equation, they act on charges, Lorentz forces, so on and so forth. When you do a principle theory, you don't have to start from the basics. You can start from the end. Okay? The velocity of light is the same in all references. What is light? What is references? You don't need to say it. Okay? The same. So in a principal theory, you can use notions which are not fundamental, which are high-level notions. So I think you can formulate quantum mechanics as a principal theory in terms of information, meaning that then you have to fill it up with the actual quantum theory in which you say, what are your variables, what you're talking about. Okay? Given these caveats, information theory is wonderful to talk about quantum mechanics, and I want to, in my 96 paper, I wrote two postulates, in fact 3 postulates, totally in terms of information theory, and said I believe that from that one can reconstruct the Hilbert space language of quantum mechanics entirely, the creator of one. And I attempted the reconstruction using quantum logic sort of technology, sort of failing. And then there have been a number of attempts in the years, and I think that the last version, which is due to Philip Hon, it's pretty good because it has a list of very simple postulates written in terms of information theory, out of which, at least for a system with a finite number of degrees of freedom, you can reconstruct the Hilbert space formalism. I don't want to go through that. It's a lot of technology. It's a very technological, mathematical part. But I want to tell you what are the 2 main postulates that I wrote down, because independently, Zeilinger, in his papers of the 97, 90, same time, independently, came out with the same 2 postulates with Buchner. But whatever. And the 2 postulates are the following. And in some non-technical sense, I do think that this captures the core of quantum mechanics. You have to add some specifications, but the core is here. And they're written in terms of information theory, and the way I write it is for a system with a finite number of, finite system, say finite number of qubits or something like that. So the first postulate is that the relevant information about the system is about the system, say 1, it's finite. Now I have to say what is relevant information, and what exactly do I mean by relevant information here. By relevant information, I mean the following. Suppose I measure the spin of a spin 1/2 particle. Okay? I measure spin 1/2 in the z direction. Then I can predict the probability distribution of the spin in any other direction. Right? Now suppose I measure again spin up in the, I don't gain anything. I have the same information as before. So having measured twice, spin up doesn't add information. So the previous one is not relevant. Of course, if a system with a higher number of degrees of freedom, to get to the maximum number of the maximum information, I have to measure many things. Okay? For an atom, I have to measure the energy, for hydrogen atom state, and the angular momentum, the z component of the angular momentum, then I'm done. Okay? So by relevant information, I mean the list of the previous measurements, okay, all the previous measurements, restricted to the one which are not irrelevant for potential in the future. Okay? And the claim is that there is a finite amount of information that I can get. Now, that seems pretty stupid because every finite system has a finite amount of information. The point is that when you put it together with the second postulate, which is I can always get new relevant information from a system. That's the second postulate. Now it seems in contradiction, but it's obviously not in contradiction because of the relevant. If I measure spin out in the z direction, and then I make a measurement of the spin in another direction, or some angle, or in the x direction, okay, I gain new information. Suppose I measure the spin in the x direction, because now I know for sure, for instance, that if I measure the spin in the x direction, once again. Okay. But in doing so, I've gained new information, but in doing so, the previous information becomes irrelevant. I erase the effect of the previous information in my ability to predict in the future. Okay? And that's never true for a classical system. In a classical system, I can either learn more about the system, more and more and more and more. If I get a maximum, that's it. I cannot get new information. I cannot make it irrelevant previous information. Now it turns out that from that plus a number of details, ask Philip, you can get Hilbert spaces, self-adjoint operators, eigenvalues, Born rules, and else. So in this sense, what was the effort here? The effort is we learn quantum mechanics. So quantum mechanics is not wave function of Schrödinger equation. We learn quantum mechanics from textbooks with this heavy formalism, Hilbert space, eigenvalues, transition amplitudes. Can we translate that in a number of simple statements about the world, the way Einstein derived the Lorentz transformation from just speed of light and relativity of velocity? Can we do something similar? To a good extent, all this complicated machinery can be translated in a few simple properties that the information we can gather about system have, these two being the main ones. I don't have much more time. I have all sorts of things I wanted to say, but let me just go fast about them. I guess I want to say something about realism because, and this I've said already, and something about at a specific point about time reversal, which is something related to what. So one general consideration and one technical consideration, then I stop. So one of the one of the main objections against the relational integration is that it's non-realist. I don't believe it's non-realist, or at least realism, and this is a series of lectures about realism. Realism is a very vague word, okay? Depending what you mean by realism. So you can be a non-realist by thinking that it's all in the mind and there's nothing outside. That's one way to be non-realist about definitely, relational quantum mechanics is not non-realist in that sense. Very realist. Here there is a world there, a system, they interact, properties are true. A relation, like a true or false. So, in this weak sense, it's strongly realist. relational quantum mechanics. Much more than cubitism or sort of single perspective view of quantum mechanics. There is no subject with respect to which quantum mechanics is. So in this sense, relational quantum mechanics is realist. In fact, I mentioned naturalism. What do I mean by naturalism here? By naturalism, I mean the idea that everything that has to do with us knowing the world, knowledge, and with us in particular, we expect to be able to understand in terms of natural sciences and in terms of the way we describe the rest of the world. So it's the idea that we are part of nature and we're not outside nature. Okay? So it doesn't mean that we know how to construct a brain and we know how consciousness works, but it means that we want a theory where we think it's possible, in principle, that we are just one of the many things in nature around. Okay? If you do that, in a sense, this is the philosophical underpinning of relational quantum mechanics. You want the subject that has information to be one of the many possible systems around. Okay? That's all. So it's relational quantum mechanics is strongly naturalist in that sense. In a sense, more than most other, many other alternatives. However, the realism of relational quantum mechanics is weakened by relationism. If by realism you mean that you expect that it's possible to describe the world at every moment of time by giving an objective value of a number of variables described in the world, which are objectively fixed, and true at every time, then in this sense the theory is not realistic. Okay? Why is it not realistic? Because the values of variables are only relational. And be careful, because even the fact that Q2 is equal to A with respect to 2, this is a relational statement as well. So you can only talk about a combination of perspectives, one for each point of view. You cannot talk about the world from outside. You cannot make a map of all possible lines. And that's what makes relational quantum mechanics, I would say, not universally accepted. Not everybody jumps up and says, oh yeah, that's a solution. Because there is this the sense of unease by not having a full map of the world written down there, which you do have in Gaussian mechanics, you do have in many world interpretation, you do have in the collapse picture. Right? You have a wave function, the wave function evolves, and you expect somehow you have other problems, you have other difficulties, but you have a strong realism, and you say that's what it is. It's a wave function in the space of the configuration of fields on web. Here, you avoid all the other problems, but you have to deal with this relationality. Now, relationality is its core in physics since Galileo. Okay, velocity is not a property of one object. Velocity is a property of two objects. One with respect to the other. My velocity is 0 with respect to the Earth, it's 11 kilometers per second with respect to the Sun, and so on. So there's nothing wrong in relational properties, but even velocity was hard to digest. I mean, if you read Newton, even Newton had difficulty of truly digesting. In fact, the way you could keep everything is not the absolute definition of velocity. And then a theorem that says you cannot measure it. Somehow there's a preferred direction. So it seems to me that relational aspects are core in modern physics, and that's what quantum mechanics is telling us. One of the reasons I like relational quantum mechanics, it works well in quantum gravity, but I'm not going into that. works better, in my opinion, than other. I wanted to talk about time reversal environments, but I think we are tired, and it's minus 10, so we'll pick up other questions on tomorrow, discussion tomorrow. There are many other things, there are other papers written on this subject. I just wanted to give you the basis, so I'll stop here.
So thank you very much for the nice lecture. There will be snacks in the back, and we'll have 20 minutes break now, and then we can start. So we will begin now with questions. First, I have to announce something about the exam. There were some questions. So the literature will be provided after this weekend. So during this weekend we will upload it all. It will be essay questions.